Hello, I'm going to give you a lecture about lecture note 21, isentropic efficiencies. But before I give you a lecture about lecture note 21, I really would like to give you a brief review of what we learned in lecture note 20. Um, I really would like to emphasize that what we learned in lecture 20 is really important to understand better about lecture 21. So please pay attention to it. What you learned in lecture 20 is basically the comparison of reversible heat and reversible work versus actual heat and actual work. So in that case, actual means irreversible. Now, we derived the shown equation for heat. The actual amount of heat transfer equals to the reversible amount of heat transfer minus T times delta Sg. But what is important thing to remember is that the default sign of heat transfer when we defined earlier is positive when we think about heat transfer in. So this equation intrinsically, is true for heat transfer in. Okay, so let me rewrite the same equation by emphasizing that is heat transfer in. So the actual amount of heat transfer in should be actual reversible amount of heat transfer in minus T delta Sg. Okay. Now, let's try to think about your system surrounded by your surroundings. And now, the temperature of surroundings is defined as T sub SUR. So then if you use this surrounding temperature, then this infinitesimal equation can be rewritten as QA in the actual heat transfer in should equal to reversible heat transfer in minus T surroundings times Sg. So what does this equation tell you? Now, if you really think about, the system, basically the heat is transferred from the surroundings to the system, then the actual amount of heat transfer is always smaller than the reversible heat transfer, and that difference is actually here can be calculated by T surrounding times total entropy generation. Now, how about your system loses heat to the surroundings? In other words, heat transfer out. Then we can rewrite that equation by using a new sign where we have minus delta Q actual out should equal to reversible heat out minus T delta Sg. Or in a total formulation, the total amount of heat transfer for the actual process out should equal to, here we have to put minus sign again. Then reversible heat transfer out plus T surroundings times total entropy generation. So when there is a heat transfer out from your system to surroundings, which is not actually desirable, heat loss is not good. When you think about this kind of the undesirable case, always the actual heat transfer or actual heat loss is greater than the reversible heat loss, and the difference between these two can be calculated by T surroundings times entropy generation. So let's try to think about the reversible work and actual work. now we have this equation that compares the actual work and reversible work. The actual work equals to the reversible work minus T delta Sg. But you have to remember again that the default sign of, the positive sign of work is always heat work out or work production. So when you think about work output, we can write equation as this, right? Reversible work out minus T delta Sg. So by using the same notation as the previous slide, what you can write is that actual work out or actual work done by the system equals to reversible work done by the system minus T surroundings times total entropy generation. Now, when you think about a device or system that does the work, so a good example is a turbine. Okay, so for that case, the actual amount of work that is done by that system is always smaller than the reversible, the ideal, the amount of work done by the system. And the difference can be calculated by same way, T surroundings times Sg, entropy generation. We can do the same thing for work in. What does it mean? Work in basically means that your system needs a work. So compressor, a pump, those kind of things are a good example of that case. So when your system needs certain work to be operated, then the top equation can be rewritten by having negative sign that delta WA equals to minus delta W reversible minus T delta Sg, or W, in the case, let's just say in and in. So the actual work that your system needs equals to reversible work that your system needs plus T surroundings times entropy generation. Okay? So when your system needs to work, the compressor or the pump, always your actual work that you need is greater than the work that you would need for the ideal case, and the difference is again T surroundings by entropy generation, right? So depending on your system, depending on your condition, and entropy, depending on the entropy generation, basically you basically lose certain things, and that is not good. Many times when you focus on work, these T surroundings times entropy generation is called many times lost work. Okay, and many times I'm going to use this term as well. But if you really think about heat case, the same term, exactly same expression is used to compare the actual heat and reversible heat. So sometimes it doesn't make sense to just say that term, T surroundings by times Sg, called as lost work. In order to make a general kind of concept, we now can call that as irreversibility. Okay, and in a symbol we use I, and its unit is kilojoule. Same way we can define irreversibility rate, which is in the unit of kilowatt, or small I, that is irreversibility per unit mass. But what those terms commonly talk about is that how the entropy generation basically make all your performance of devices worse. Okay, and exactly by this amount of amount of irreversibility, you get certain things being lost. Okay? So that is a really, really important part that you have to remember.